Alright, so we're gonna continue with our reinforcement learning stuff, and let's pull up the code. Here it is. So last time we said, how can we have greater pleasure or discomfort for a computer system? We probably need to reward the number of won games over an interval. This is an understandable confusion because these networks use error information to update connection rate, but these all I copy this by this substance essential of trial and error. Emphasis on learning from a teacher. Probably need to play myself a few rounds. Least mean square. Criticizing some random move and taking rewards away. Mixing data and guessing in. What's that mean? Linear reward system. So yeah. That one because we want to say shouldn't have a linear system of rewarding things. So just don't keep it. Just maybe don't give it one. Maybe if it's losing, then it needs more change. If it keeps losing, it needs more change. I don't know. Almost. If it is losing, then it needs more. If it's losing, then it's more punishment. Exponential punishment. What if in the path of losing we punish, and then the path of losing might have resulted to a better end? So the limit to our reward system has system that's possible. Compare later. Yeah. So maybe close to modification, open to addition. Addition. Okay. And so the bibliographical remarks, we don't need that probably. Let's just take a look at it. Maybe we do. Just taking a look at these. This is recording. Are we recording? Are we recording? Yes, we're recording. Okay. And how's the font on this? I feel like yeah, that's good enough. Right. Discrete time step. T is final time step of an episode. State at T, action at T, for the T. Word T. Alright. Oh yeah, the blue. Oh, maybe we should read this exercise. The example of Phil's breakthrough in this chapter was inspired by Agree. We directly read it to chapter 6 for references to the kind of temporal difference method we use in the tic-tac-toe example. Self-play. Suppose instead of playing against a random opponent, the reinforcement learning algorithm described above played against itself. Well, it depends. If I have two exactly same system, everything doesn't work like that. Because there's a level of turn in any two-player game that one takes a move, the other one takes another move. Symmetries. Many tic-tac-toe positions appear different but are really the same because of symmetries. How might we amend the reinforcement learning algorithm described above to take advantage of this? In what ways? Would it? Oh. I agree. Symmetries. Yeah. If you have, so like if the player puts in the middle, you go up. It's literally the same as putting it. So some things are exactly the same. Some positions are exactly the same. Some positions are sort of the same. Just have this. Alright, greedy play. Suppose the reinforcement learning player was greedy, that is, it always played the move that brought it to the position that it rated the best. Would it learn to play better or worse than a non-greedy player? What problems? Well, it definitely has problems with its planning. It depends on the game. Sometimes. It depends on the game. I don't remember like some games that the optimal strategy is to be greedy, but depends on the game. If it doesn't need to plan, then yeah. But greedy is sort of like you take the highest in a time interval. So maybe if you just change your time interval and you're greedy, then you're just dynamically better. But yeah, a lot of greedy algorithms basically just the next step. So I see. That's the situation that happens. Okay. Learning from exploration. Suppose learning updates occurred after all moves, including exploratory moves. If the step size parameter is appropriately reduced over time, then the state values would converge to a set of probabilities. What are the two sets of probabilities computed then? When we do and we do not learn from exploratory moves. Assuming that we do continue to make exploratory moves, which set of probabilities might be better to learn, which will result in more wins. If the step size parameter is appropriately reduced over time, in the state values will converge to set of probabilities. What are the two sets of probabilities computed when we do and we do not learn from? Seriously, don't understand this question. What are the two sets of probabilities computed when we do and we do not learn? So the so we should converge to set of probabilities, which I kind of see. Assuming that we do continue to make exploratory moves, which set of probabilities might be better to learn, which will result in more wins. I'm not getting this. Let's skip this for now. Other improvements. Can you think of other ways to improve the reinforcement learning player? Can you think of a better way to solve the tic-tac-toe problem, I suppose? about the trial and error and a model based. So I kinda agree with just, I don't know. You need to know how much computation is possible, and you probably need to learn some generalization from before and combine those two. I mean, the more specified your generalization can get, the better. If you can have it make decisions, help you deduce the stuff, but because in order for a system to know how to value a position, it's basically having it played some random moves, and then a randomness converges to some stuff, right? A randomness should converge because our environment is closed, especially if it's a game. But if our environment is not closed, yeah, so for robotics maybe we have, is it for, I think robotics we had more constraints on the environment. I think it should work just 100% way better. Those are just some random thoughts. Yeah. Alright, so tabular solution methods. Let's go over this. In this part of the book, we describe almost all the core ideas of reinforcement learning algorithms in their simplest forms, that in which the state and action spaces are small enough for the approximate action value function to be represented as an array or table. In this case, the methods can find exact solutions, that is, they can often find exact the optimal value function and the optimal policy. This contrasts with the approximate methods described in the next part of the book, which only can find approximate solutions, but which in return can be applied effectively to much larger problems. The first chapter of this part of the book describes solution methods for the special of the reinforcement learning problems in which there is only a single state called bandit problems. The second chapter describes the general problem formulation that we treat throughout the rest of the book: finite Markov decision processes. And its main ideas include Bellman equations and value functions. The next three chapters describe three fundamental classes of methods for, interesting. Very, very interesting. The next three chapters describe three fundamental classes of methods for solving finite Markov decision problems: dynamic programming, Monte Carlo methods, and temporal difference learning. Each class of methods has its strengths and weaknesses. Dynamic programming methods are well developed mathematically but require complete and accurate model of the environment. Monte Carlo methods don't require a model and are conceptually simple, but are not suited for step-by-step incremental computation. Finally, temporal difference methods require no model and are fully incremental, but are more complex to analyze. The methods also differ in several ways with respect to their efficiency and speed of convergence. The remaining two chapters describe how these three classes of methods can be combined to obtain the best features of each of them. In one chapter, we describe how the strengths of Monte Carlo methods can be combined with the strengths of temporal difference methods via the use of eligibility traces. In the final chapter of this part of the book, we show how these two learning methods can be combined with model learning and planning methods, such as dynamic programming, for a complete and unified solution to the tabular reinforcement learning problem. Okay, multi-R bandits. Excuse me. The most important feature distinguishing reinforcement learning from other types of learning is that it uses training information that evaluates the action rather than the actions taken rather than instructs by giving correct actions. This is what creates the need for active exploration, an explicit trial and research for good. Oh, maybe I shouldn't play with it. For good behavior, purely evaluative feedback indicates how good the action taken is, but not whether it is the best or the worst action possible. Evaluative feedback is the basis of methods for function optimization, including evolutionary methods. Purely instructive feedback, on the other hand, indicates the correct action to take independently of the action actually taken. This kind of feedback is the basis of supervised learning. Right. Which includes large parts of pattern classification, artificial neural networks, and system identification in their pure forms. These two kinds of feedback are quite distinct. What about unsupervised? What if you just let it run? You try hashing it in some way, and basically it recognizes that position because it has some sort of, so we have some space, which is the space that we have, and we try to reduce that space to whatever we can have. Well, we see. Evaluative feedback depends entirely on their action taken, whereas instructive feedback is independent of the action taken. There are also interesting intermediate cases in which evaluation and instruction blend together. In this chapter, we studied the evaluative aspect of reinforcement learning in a simplified setting, one that does not involve learning to act in more than one situation. The non-associative setting is the one in which most prior work involving evaluative feedback has been done, and it avoids much of the complexity of the full reinforcement learning problem. Studying this case will enable us to see most clearly how evaluative feedback differs from and yet can be combined with instructive feedback. The particular non-associative evaluative feedback problem that we can explore is a simple version of an armed bandit problem. We use this problem to introduce a number of basic learning methods, which we explain in later chapters to apply to the full reinforcement learning problem. At the end of this chapter, we take a step closer to the full reinforcement learning problem by discussing what happens when the bandit plays problem becomes associative. That is, when actions are taken in more than one situation. An unarmed bandit problem. Consider the following learning problem. You are faced repeatedly with a choice among n different options or actions. After each choice, you receive a numerical reward chosen from a stationary probability distribution that depends on the action you selected. Your objective is to maximize the expected total reward over some time period, for example, over 100 action selections or time steps. This is the original form of the unarmed bandit problem, so named by analogy to a slot machine or one-armed bandit, except that it has n levers instead of one. Each action selection is like a play of one of the slot machine's lever, and the rewards are the payoffs for hitting the jackpot. Through repeated action selections, you are to maximizing your winnings by concentrating your actions on the best levers. Another analogy is that of a doctor choosing between experimental treatments for a series of seriously ill patients. Each action selection is a treatment selection, and each reward is the survival or well-being of the patient. Today, the term unarmed bandit problem is sometimes used for generalization of the problem described above. But in this book, we use it to refer just to this example, to this simple case. In our unarmed bandit problem, each action has an expected or mean reward given that action is selected. Let us call this the value of that action. If we knew the value of each action, then it would be trivial to solve the unarmed bandit problem. You would always select the action with highest value. We assume that you do not know. Oh my god. Do not know the action values with certainty, although you may have estimates. If you maintain estimates of the action values, then at any time step there is at least one action whose estimated value is greatest. We call this a greedy action. If you select a greedy action, we say that you are exploiting your current knowledge of the values of these actions. If instead you select one of the non-greedy actions, then we say you are exploring, because this enables you to improve your estimate of the non-greedy action's value. Exploitation is the right thing to do to maximize the expected reward on the one step, but exploration may produce the greater total reward in the long run. For example, suppose the greedy action's value is known with certainty, while several other actions are estimated to be nearly as good but with substantial uncertainty. The uncertainty is that it's such that I don't know why this is so hard to read. At least one of these other actions probably is actually better than the greedy action, but you don't know which one. If you have many time steps ahead on which to make action selections, then it may be better to explore the non-greedy actions and discover which of them are better than the greedy action. Reward is lower in the short run during exploration but higher in the long run, because after you have discovered the better actions, because after you have discovered the better actions, you can exploit them many times. Because it is not possible both to explore and to exploit with any single action selection. One often refers to the conflict between exploration and exploitation. In any specific case, whether it is better to explore or exploit depends in a complex way on the precise values of the estimates, uncertainties, and the number of remaining steps. There are many sophisticated methods for balancing exploration and exploitation for particular mathematical formulations of the n-armed bandit and related problems. However, most of these methods make strong assumptions about stationary and prior knowledge that are either violated or impossible to verify in applications. In the full reinforcement learning problem that we consider in subsequent chapters, the guarantees of optimality or bounded loss of these methods are of little comfort when the assumptions of their theory do not apply. Alright, so I just understood nothing. Depends entirely on the action taken, whereas instruct feedback is independent there. So in this case, for enables to see most clear how evaluative feedback differs from, and it can be combined with instructive feedback. Expected reward on the one step, but exploration may produce the greater total reward in the long run. For example, suppose the greedy action's value is known with certainty while several other actions are estimated to be nearly as good but with substantial uncertainty. Uncertainty is such that at least one of these other actions probably is usually actually better than the greedy action. Alright, let's just move on. In this book, we do not worry about balancing exploration and exploitation in a sophisticated way. We worry only about balancing them at all. In this chapter, we present several simple balancing methods for the n-armed bandit problem and show that they work much better than methods that always exploit. They need to balance exploration, and exploitation is a distinctive challenge that arises in reinforcement learning. The simplicity of the unarmed bandit problem enables us to show this in a particularly clear form. Alright, the particularly clear form. We begin by looking more closely at some simple methods for estimating the value of functions and for using the estimates to make action selection decisions. In this chapter, we denote the true actual value of actions A as Q of A and the estimated value on the T TF time step as QTA. Recall that the true value of an action is the mean reward received when that action is selected. One natural way to estimate this is by averaging the reward actually received when the action was selected. In other words, if by the TF time step action A has been chosen and TA times prior to T, yielding rewards R1, R2, R and T of A, and those are the rewards, then its value is estimated to be what was Q again? Around Q. Estimate of random variable of Q. Value of taking action A state in sometimes it doesn't. Oh, Phil is the breakfast guy. And each action selection is like you play that, the aim bandit, that, we go to here, the value of Q under state aim with value of that. F and T A equals 0, then we define QT instead of some default values such as Q1A equal to 0 as NTA going to infinity. RL rotations. So have a bunch of values and then get rewards for having some values. Interesting. Formalism. Sometimes in RL we don't need to discover how good an action is in an absolute sense, but only how much better it is than others on average. That is to say, we want to know the relative advantage of that action. We make this concept precise with the advantage function. The advantage function corresponding to a policy pi describes how much better it is to take a specific action A in state S over randomly selecting an action according to pi dot if S, assuming you act according to pi forward after. Mathematically, the advantage function is defined by that. So far, Markov decision processes. An MDP is a 5-tuple where S is set of all valid states, A is the set of all valid actions, and R is the reward function with RT is equal to reward at the state at that action and going to the state of the next state, taking some action. And P is the transition probability function with P S prime given S and A being the probability of transition into S state. S prime if you start in states S, take action A, and rho is the starting state distribution. And how can we use the distributions? I don't know. Okay. Just move on. By the law of large numbers, Q of TA converges to QA. Call this the sample average method for estimating action values because each estimate is simple average of the sample of relevant rewards. Uh, of course, this is just one way to estimate action values and not necessarily the best one. Nevertheless, for now, let us stay with this simple estimation method and turn to the question of how the estimates might be used to select actions. Simplest action selection rule is to select the action or one of the actions with the highest estimated action value. That is to select as step T one of the greedy actions, A optimal was for which QT A optimal T is equal to max A QT of A. This greedy action selection method can be written as R max. So whatever given A max should be equal to A at T, where argmax denotes the value of A at which the expression that follows is maximized, which ties broken arbitrarily. Greedy action selection always exploits current knowledge. Okay, gonna do 5 pages. Yes. It spends no time at all sampling apparently inferior actions to see if they might really be better. A simple alternative is to behave greedily most of the time, but every once in a while, say with a small probability E, instead to select randomly from amongst all the actions with equal probability independently of the action value estimates. We call methods using this near greedy action selection rule E-greedy methods. An advantage of these methods is that in the limit, as the number of plays increases, every action will be sampled an infinite number of times, guaranteeing that NT-A going to infinity for all A, thus ensuring that the probability of A converge to QA. This of course implies that the probability of selecting the optimal action converges to greater than 1 minus E, that is to near certainty. These are just asymptotic guarantees, however, and say little about the practical effectiveness of the methods. To roughly assess the relative effectiveness of the greedy and e-greedy methods, we compared them numerically on a suite of test problems. This was a set of 2,000 randomly generated and armed bandit tasks with n equal 10. For each bandit, the action values Q of A equal 1 to 10, were selected according to a normal Gaussian distribution with mean 0 and variance 1. On the TF time step with a given bandit, the actual reward RT was the QAT for the bandit, where AT was the action selected. Thus, a normally distributed noise term that was mean 0 and variance 1, averaging over bandits. We can plot the performance and behavior of various methods as they improve with experience over 1,000 steps. We call this suite of test tasks the 10-armed test bed. Figure 2.1 compares the greedy method with two e-greedy methods, E equals 0.01 and E equal 0.1 as described above on the 10-arm testbed. Both methods this. Average performance of epsilon greedy action value methods on the 10-armed testbed. These data are averages over 2,000 tasks. All methods used sample averages as their action value estimates. The detailed structure at the beginning of these curves depends on how actions are selected, but multiple actions have the same maximal action value. Here, such ties were broken randomly. An alternative that has a similar effect is to add a very small amount of randomness to each of the initial action values, so that ties effectively never happen. Alright, I'm a little bit slow today. This seriously should be studied by some psychologist, but I don't know, so we're gonna cut this short, come back tomorrow a little bit better, and then go probably, hopefully 15 pages. And also I'm gonna do a review, watch my videos again, do a little bit of research on this site so I can explain these to the camera and then get a little bit better. So see you in the next video.